After studying this module, you shall know about the free radical substitution on aromatic systems, learn about the different types of reactions involving free radical mechanisms on aromatic substrates, analyze addition reaction mechanisms on the aromatic substrates, understand the coupling of alkynes, know about the diazonium salts and their free radical reactions, and the Sandmeyer reaction and its mechanism. He observed in 1934 that thermal decomposition of diazonium salts in aromatic solvents led to the arylation of aromatic rings. These results were explained by the mechanism involving the homolysis of ionized salts to provide aryl radicals, which directly displaced a hydrogen atom in the aromatic solvent molecule. An aryl halide led to the formation of an halogen radical and nitrogen was expelled in the given reaction. The aromatic radical obtained combined with the benzene or the phenyl substituent to form the aryl substituent plus the hydrogen radical was eliminated. Similar results were obtained when the aryl radicals generated from the decompositions of the benzoyl peroxides in the aromatic solvents. Here, the decarboxylation took place along with the generation of a phenyl radical. Aromatic systems behave differently than the aliphatic systems towards the free radical reactions. In this module, we shall discuss about the various reactions that the free radicals undergo with the aromatic substrates. Due to attention that shall be paid to the reaction mechanisms and also the factors affecting such reactions. Factors affecting free radical reactivity in the aromatic substrates. All substituents increase reactivity at ortho and para positions over that of benzene. There is no great difference between the electron donating and the electron withdrawing groups. Reactivity at meta positions is usually similar to that of benzene, perhaps slightly higher or lower. This in fact, coupled with the preceding one, means that all these substituents are activating and ortho-para directing. None are deactivating or chiefly meta-directing. Reactivity at ortho positions is usually somewhat greater than at para positions, except where a large group decreases orthoreactivity for steric reasons. Substituents have smaller effect than in electrophilic or nucleophilic substitutions. General mechanism of the free radical reactions at an aromatic substrate. In the reaction of free radicals at aromatic substrates, some general steps involved in the mechanism are: in the first step, the radical attracts the ring in much the same way as would an electrophile or a nucleophile. The radical formed is resonance stabilized, as can be seen from the resonating structures shown in the given figure. Radical can undergo coupling to give the 2 product or may undergo disproportionation to give the 3 product, or can undergo the removal of hydrogen free radical to form a biaryl. Free radical substitution SN1 reaction on aromatic system. Free radical substitution at an aromatic carbon seldom takes place by mechanism in which the hydrogen is abstracted to give an aryl radical. Usually, the mechanism is similar to that of an aromatic electrophilic and nucleophilic substitutions. For example, in the reaction of a thionyl chloride with optically active alcohol, the first step is same as SN1 ionization, in which the leaving group and the residue dissociate and form a tight ion pair. In the second step, the part of the leaving group attacks the incipient carbocation from the same side. That is, the chloro group attacks from the same side, that is the front side from where the oxygen is leaving. In the presence of pyridine, the Walden inversion takes place according to the mechanism. Here, the attack takes place from the side opposite to the side from where the leaving group goes. As a result, the inversion of configuration takes place, leading to Walden inversion. Free radical addition reaction on aromatic system. Benzene is increasingly susceptible to radical addition reactions, that is, it is to electrophilic addition. Note that benzene does not react with chlorine or bromine in the devoid of catalyst and heat. In the presence of a strong sunlight or with the radical initiators, benzene adds these halogens to yield hexacyclohexanes, 9 stereoisomers. The addition of chlorine is depicted here. The 2 of the 7 mesostereoisomers, as can be seen, the isomers primarily differ in their position, the axial and the equatorial positions of the hydrogens and chlorines. Benzene in the presence of sunlight and 3 molecules of chlorine lead to the formation of benzene hexachloride. First prepared in 1825, benzene hexachloride's insecticidal properties were identified in 1944 with the gamma isomer, which is about 1000 times more toxic than any of the other diastereomers formed in the reaction. The orientations of the chlorine atoms with respect to the ring of the carbon atoms are the structural differences between these individual isomers. Free radical oxidation reactions on aromatic system. In the previous module, we have studied in detail the topic of auto-oxidation. Here, we try to put some more light on this topic using the aromatic systems. Compounds specially susceptible to auto-oxidation are benzylic and allylic compounds as well as ethers, amines and similar compounds containing heteroatoms. All these compounds readily form radicals. Auto-oxidation is a process that has practical consequences too. For example, the main cause of food spoilage are microbial, mold and bacteria, and auto-oxidation. Since auto-oxidation takes place in so many foods, food processors add antioxidants to the food or packaging materials. Using an antioxidant gives food a longer shelf life by preserving the taste and the nutrient levels. The antioxidants that food processors commonly use are BHA and BHT. BHA, which is butylated hydroxyanisole and is a mixture of 2 and 3 tertiary butyl 4-methoxyphenol. BHT is an acronym of butylated hydroxytoluene and is 2,6-di-tertiary butyl 4-methoxyphenol. Both BHA and BHT form resonance stabilized phenoxy radicals with oxygen or other radicals. These phenoxy radicals then react with hydroperoxide radical to form a dienone. The structures below are generalized for both BHA and BHT as the mechanism of both are identical, and as a result of this they tend to behave like an antioxidant. We can see here the molecule tends to undergo a cleavage forming a phenoxy radical and a hydroperoxide. This phenoxy radical undergoes resonance stabilization leading to the formation of a radical at the para position carbon atom, which in turn combines with the hydroxy peroxide forming the given compound. free radical reduction reactions on the aromatic system. A radical reduction reaction generally involves the addition of hydrogen to a pi bond. The reduction reaction types that you studied previously were catalytic reductions, some ionic reductions, and one radical reduction. To proceed, a radical reduction reaction requires a source of electrons. Some of the older methods for reducing organic compounds and used metals, especially alkali metals, as they are a good electron source. To make the electrons from the alkali metal available, the reaction needs some solvent that dissolves the metal. The solvents most commonly used are alcohols and liquid ammonia. Because the reaction proceeds by dissolving the metal in the solvent, the chemists call this reaction as a dissolving metal reaction. However, since the introduction of metal hydrides, dissolving metal reactions are not used very often anymore. The Birch reduction offers access to substituted 1,4-cyclohexadienes as shown in the given mechanism. An electron source from the alkali metal leads to the formation of an anion which reacts with the alcohol, abstracting out a proton, and again an electron source leads to the formation of another anion, and next abstraction leads to the formation of a diene structure. Reactions of arenes with plus I, that is plus inductive effect, and the plus mesomeric substituents lead to the products with the most highly substituted double bonds. Electron withdrawing substituents have different effects on the Birch reduction, and the effect changes appreciably with the substituents. Taking an example of the reaction of benzoic acid, which leads to the formation of 2,5-cyclohexadiene carboxylic acid. This observation can be rationalized on the basis of carboxylic acid stabilizing an adjacent ion, as a result leading to the formation of the given product. Alkene double bonds are only reduced if they are conjugated with arene, and occasionally isolated terminal alkenes will be reduced. Coupling reactions involving free radicals. Firstly, the coupling of alkynes. The coupling of acetylene and mono-substituted acetylenes is catalyzed by copper in two oxidation state complexes. This yields dienes in the presence of suitable base such as pyridine. The probable route of the reaction is via 1 electron oxidation of the acetylide anion by copper 2 ion. This is followed by dimerization of the resulting acetylide radical. As can be seen, the base abstracts out a proton radical forming an anion, which in the presence of the copper 2 oxidized complex leads to the formation of a acetylide radical, which undergoes dimerization with another such molecule, forming a dimer product. An alternative synthetic strategy has been employed using an aqueous mixture of copper 1 chloride and ammonium chloride under air. These conditions facilitate the removal of proton by complexing between carbon-carbon triple bond and copper 1 ion, as shown here in the given mechanism. Some of the copper 1 could be oxidized to copper 2 as the reaction functions under air, which in turn could oxidize the acetylide ion to the acetylide radical. This has the ability to dimerize to yield di-ions as shown earlier. Various synthetic applications are reported in this context. For example, synthesis of phenolgenic acid has been achieved from the undecylenic acid. Intramolecular coupling of terminal alkynes may occur also in some cases to produce cyclic compounds if the resulting ring is not highly strained. For example, the synthesis of macrocyclic lactone exaltolide. This compound is partly responsible for the sweet odor of the Angelica root have been achieved with high yield. Coupling of monosubstituted acetylene with 1-bromoalkyne can be performed to afford heterocoupled product in good yields. Coupling reaction of diazonium salts. Diazonium compounds represent a large group of organic compounds with general formula R N2 plus X minus, in which R can be alkyl or aryl and X is an organic or inorganic anion such as halogen. The diazonium salts, especially those where R is an aryl group, are important intermediates and have found wide applications in organic synthesis. Let us discuss few of them. Arylation of aromatic compounds by diazonium salts. When the normally acidic solution of diazonium salt is made alkaline, the aryl portion of the diazonium salt can couple with another aromatic ring known as the Gomberg or Gomberg-Bachmann reaction. It has been performed on several types of aromatic rings and on quinones. Yields are not very high, usually less than 40%, because many of the side reactions undergone by the diazonium salts, although high yields have been obtained under phase transfer conditions. A rapid and convenient way to diazotize the amine substrate uses isopropyl nitrite in the presence of sodium iodide, in which case the ring closed product is formed in one step. Palladium catalyzed arylation of arene diazonium salts are also known. The mechanism involves the generation of an aryl radical from a covalent azo compound. In the acid solution, diazonium salts are ionic and their reactions are polar. When they cleave, the product is an aryl cation. However, in neutral or basic solution, diazonium ions are converted to covalent compounds and these cleave to give free radicals, aryl radical and the Z radical. Under Gomberg-Bachmann conditions, the species that cleaves is the anhydride. The aryl radical thus formed attacks the substrate to give the aryl cation intermediate, which is product number 3, from which the radical 2 abstracts the hydrogen to give the product 4. N-nitrosoamides probably rearrange to N-acyloxy compound number 5, which cleaves to give aryl radicals. There is an evidence that the reaction with alkyl nitrides also involves attack by the aryl radicals. The score reaction can take place by two different mechanisms depending upon the conditions. First, attack by an aryl radical as in the Gomberg-Bachmann reaction, or second, attack by an aryl cation similar to the SN1 mechanism. Under certain conditions, the ordinary Gomberg-Bachmann reaction can also involve the attack by aryl cations. Reactions of arene diazonium ions. The reaction between copper salts and arene diazonium ions are also believed to involve free radicals. In these reactions, the free radicals are generated in the first step by cuprous ion reduction of the diazonium ion. The cuprous ion is then regenerated in the final step as the product is formed. As can be seen in the steps, aromatic diazonium ion with copper plus forms aromatic diazonium radical and copper 2 plus by taking up an electron from the metal. This further undergoes a cleavage by the release of nitrogen, forming an aryl radical. Aryl radical again combines with the copper halide to form ArCuX, which then in turn leads to the sequence of reactions forming the aromatic halide and the two copper plus ions. The reaction with water, on the other hand, may actually be an SN1 reaction involving the highly energetic phenyl cation as an intermediate. Here what we see is that a nitrogen is lost with the formation of a phenyl radical, wherein the water attacks to form a phenol molecule. Reactions requiring a copper ion catalyst are usually designated as Sandmeyer reactions. After Swiss chemist Traugott Sandmeyer, who discovered the synthesis of benzonitrile from phenyl diazonium chloride and cuprous cyanide, the formation of aromatic chlorides, bromides and nitriles all require the presence of a copper salt. Let us study the Sandmeyer reaction in detail. The Sandmeyer reaction is a versatile method for replacing the amine group of primary aromatic amines with number of different substituents. The amine is first converted into a diazonium salt. The diazonium salt can then undergo a substitution reaction with various reactants, particularly copper-1 substrates. Although the substitution can be simplistically viewed as a direct ionic substitution reaction, anion as a nucleophile molecular, nitrogen as a premier leaving group. It can react in the presence of NaNO2 and HCl, which produces HNO2 in situ, producing the aromatic diazonium salt, which in turn reacts with the number of reagents producing aromatic cyanides, halides, phenols and aromatic hydrocarbons. Mechanism is explicitly shown in the various steps. Sandmeyer reactions, as discussed above, require catalyst of copper plus ions, but the Sandmeyer type reactions with thiols, water and potassium iodide don't require the catalysis. The Sandmeyer reaction is a very important transformation in aromatic chemistry because it can result in some substitution patterns that are not achievable by direct substitution. Fluorination is possible by using the related Sheeman reaction. Reactions involving the formation of biaryls. At relatively high pH or in non-polar solvents, diazonium ions are converted to non-ionic azo compounds. These compounds are unstable and readily decompose into aryl free radicals, which then react to give the products that differ from those of the typical substitution reactions in the acidic solution. This reaction is responsible for the reduction of arene diazonium ions by ethanol. In ethanol, diazonium ion is converted to phenyl radical, which then abstracts a hydrogen atom from the alcohol to give the aromatic hydrocarbon. In solvents such as benzene, the aromatic free radicals are trapped by the solvent to give biaryls, a reaction known as Gomberg-Bachmann-Hay reaction when intermolecular and Score reaction when intramolecular. These reactions are frequently catalyzed by copper powder and often carried out using the aromatic trapping agent as a solvent and an alkyl nitrite ester as a diazotizing agent instead of aqueous nitrous acid. To summarize, a radical reduction reaction generally involves the addition of a hydrogen to a pi bond. The reduction reaction types that you studied previously were catalytic reductions, some ionic reductions and one radical reduction. The coupling of acetylene and mono-substituted acetylenes is catalyzed by copper 2 complex. This yields dienes in the presence of a suitable base such as pyridine. Diazonium salts, especially those where R is an aryl group, are important intermediates and have found wide applications in organic synthesis. This Sandmeyer reaction is a versatile method for replacing the amine group of an aromatic primary amine with number of different substituents.